So tonight I'm going to react to a video where scientists created a new electron microscope where they actually can see atoms. I guess those of you who paid attention in science or physics, we always hear about atoms and molecules. So for the first time, they're going to zoom in and keep zooming and see what atoms look like. I'm excited to see myself. I know I sound excited.
This is a tiny piece of metal just 3 millimeters across, and here's what happens if you just keep zooming in. 1,000 times, 100,000 times, 50 million times. Each of these blobs is an actual atom. I saw this the other day at the University of Sydney, and it kind of blew my mind, because up until just 30 years ago, directly seeing atoms like this was thought to be impossible.
The rooms that you're going to see here are perhaps the most shielded rooms on campus, or even in the whole of Sydney, I would say, and perhaps also the most expensive.
That's wild.
So why is it so hard to see atoms? Well, you can't actually see atoms with visible light. That's because while light has wavelengths between 380 and 750 nanometers, an atom is still over 3,000 times smaller, just 0.1 nanometers. And if the wavelength of light is much bigger than the thing you're trying to see, the light will just diffract or bend around it, so you won't be able to see it. So if you want to see atoms, you need something with a much, much smaller wavelength. The best candidate isn't even light. It's electrons. In 1924, a French physicist named Louis de Broglie worked out that everything was sort of wave-like, not just light, but matter too. Atoms, molecules, even you yourself have a wavelength. And the formula for this wavelength is Planck's constant divided by the object's momentum, that is, mass times velocity.
So here what you actually see, that's the column of the microscope where we accelerate the 300 keV electrons down.
300 kilovolts, these electrons.
Yes. So they are relativistic particles.
How fast are they moving? 99% the speed of light, or?
Well, around 80.
80% the speed of light?
Yes.
So what would be their wavelength?
The wavelength is the Planck constant over the momentum, right? So if we calculate that, we come to around between 2 to 3 picometers.
Whoa!
Yeah.
That's over 100,000 times smaller than visible light, so theoretically, you get 100,000 times more resolution. Shortly after de Broglie's discovery, a group of scientists in Germany started working on a microscope that would use these high-speed electrons. The only problem is you can't bend electrons using glass lenses. So how do you focus them? Hans Busch, a German physicist, suggested that an electromagnetic lens might do the trick. He published his results in 1926, but never actually built one. Fortunately, a copy of his paper fell into the hands of an eager young PhD student, Ernst Ruska. Ruska built his first prototype by coiling up some wire and surrounding it with iron, taking care to leave a gap in the middle. Then, when he passed a current through the coil, it induced a donut-shaped magnetic field through the metal and across this gap. This was his lens. To test it, Ruska first boiled electrons off a tungsten filament, the same kind of filament you'd find in an incandescent light bulb. He accelerated these free electrons through a positively charged anode down to his electromagnetic lens. As an electron approaches the lens, the magnetic field exerts a force on it. So if an electron is traveling in the y direction and the magnetic fields are in the x direction, this force, called the Lorentz force, pushes it in the z direction. But as the electron moves this way, it encounters other magnetic field lines along the donut shape, which constantly point its motion in a circle. But then this circular motion means the Lorentz force starts pushing the electron inwards as well, spiraling it into the center of the lens. Now, if you trace the path of the whole beam of electrons, you'll see they all get steered into the center, focusing the beam. By 1931, Ruska and his colleague Max Knoll used this kind of design to build the first working electron microscope. It was pretty basic, made of brass roughly bolted together. But it worked. The image itself was created once the focused electron beam hit a sample sitting at the focal point. The sample needed to be incredibly thin, only around 100 nanometers.
This is interesting how light doesn't work, but they have to kind of channel electrons onto the object. Most people, I don't think recall. I think I've seen an electron microscope. Actually, looked into one once, maybe once or twice. Actually, yeah, a couple times. I'm not gonna age myself, but it was during a university. We were looking at some polymers, and this is useful just for seeing anything microscopic. But I think it does help when the objects are like really, really tiny, non-biological. Even some biological stuff is pretty small. But I thought it was interesting how they just beam all the electrons to give a reflection of the image of you're trying to see, since like they said, light is too, the wavelength is too big. I thought it was an interesting contrast.
Meters thick. More electrons would make it through the thinner parts of the sample than the thicker parts, creating an electron imprint of the sample. Then a second electromagnetic lens magnified this imprint down onto a fluorescent detector, producing the final image. This was known as a transmission electron microscope, or TEM. Now, early versions of the microscope barely magnified at all. In fact, it wasn't even better than an optical microscope. But Ruska was determined. Over the next few years, he experimented with adding more lenses onto the microscope to create bigger and bigger images. By the mid-1930s, Ruska had gotten the TEM way past 10,000 times magnification. It could produce close-ups of insects, bacteria, and even viruses at a level far surpassing the optical microscope. But right as Ruska's TEM was taking off, a German physicist named Otto Scherzer published a paper claiming that the microscope was about to hit a brick wall. There was a flaw in the electromagnetic lens, he wrote, that was completely unavoidable.
I'm going to skip past the history of electron microscopes, and we're going to get to the part where they actually can get to see the atoms. Okay, here's the part where there's a group of researchers. They actually come up with an idea to create an electron microscope that can view atoms, and this is where they discover. Actually, they weren't supported actually initially, but I won't tell the story. I'll get actually I ran ahead to see it, but I won't spoil anything.
For years, barely anyone had been interested in their research, or more importantly, in funding it. And for a good reason, too. Their idea was kind of crazy. I mean, they purposefully wanted to break the image using a lens that wasn't symmetric. Their hope was that there would be a small part of this distorted image that would be slightly diverging. And maybe, just maybe, this small part could correct the spherical aberration of the original lens. So they got to work. To distort the image, they used a massive nest of electromagnets with 6, 8, or even 10 separate coils and magnets with bumpy magnetic fields. These were known as the hexapole, octapole, and decapole magnets. So as the electron beam passed through a hexapole, it would twist and squeeze the flat 2D image into a triangular saddle. And the circumference of the original beam would be pushed into the 3 corners, with the rest of the interior stretched out. But now, the middle of the image would have a slight concave bow, giving the effect of a small divergence. Then Rose, Hayter, and Urban forced the beam through a second hexapole, one that worked the opposite way, so it would unbend the distorted image back into a circular shape. But now they calculated this new image might have the remnants of that tiny divergence still in its center, with spherical aberration pointing in the opposite way. So if they got their maths and engineering exactly right, they could feed an image with spherical aberration through these 2 lenses to almost completely counteract the effect.
And I imagine a lot of people in the field thought it was a crazy idea when it was proposed, right?
Not only the concept, but that this is like technical feasible, I believe. It was thought that this is not possible.
By May 1997, the group had just 2 months of development time left before their last sponsor withdrew their backing. And to make matters worse, their latest lens iteration was still just on the drawing board. But somehow, by the 23rd of July, just a week before their funding ran out, the new lens was ready to test. They gingerly placed it into the microscope, but like every time before it, the lens was unstable and failed. So they decided to switch off the equipment for 24 hours to allow the magnets to settle. And then at 2 a.m. on the 24th, they turned it on again. And almost magically, the picture started to stabilize. Suddenly, there was no aberration, only beautiful, clear images of atoms.
You know, it's funny how things work sometimes. You work on it, you work on it, you work on it, you get tired, and then you just say, okay, I'm going to take a break, take a nap. Sometimes this leads to a different discovery off the path of where you originally intended. And then a lot of times you just have to take a break and then your answer comes. This happens all the time, especially for you guys who are in any type of engineering, science, even IT. It's like something doesn't work and then all of a sudden it works.
After more than 60 years of failed attempts, Urban, Rose, and Hayter pulled off the seemingly impossible. With this method, they cut the resolution of the TEM down to only 0.13 nanometers. An average TEM image went from looking like this to this. A few months after the group's breakthrough, Newt Urban attended a microscopy conference to share these results. But because of the group's reputation, he was relegated to a small back room that barely anyone noticed. Soon, however, word spread that against all odds, his pictures seemed real. Then a crowd of hundreds formed. People were lining up outside, hoping to get a glimpse of their stunningly sharp images.
So we're gonna get a sample holder.
Yes, now we get a sample holder out. We put that under the optical microscope. So the sample itself is a small lamella that you can't see without the optical microscope. Yeah, have a look through that.
Beautiful. On top of the B, there's a prong.
Yeah. And on the very top of that, on the left-hand side, looks like a little bit of dust. That's our actual sample. Okay, now I simply go up with the magnification and I do a very few, like more basic alignments. In this electron microscope, because it's called transmission electron microscope, the electrons always transmit the sample. Here we look through our entire sample at the same time. And that's why it's so important that we align the sample. So if you imagine atoms in a high symmetry direction are lined up like pearls on a string, when we look down it, well, we can see an image. But if we're in like some random direction, then everything would be just blurred. So that's why we have to do some tilting in the end. And this is where the actual sample starts, the strontium titanate. And this is a thin region where we hope to get atomic resolution.
So this is 5,000 times?
Yes.
Wow.
And we see strontium, titanium, we see oxygen, we see carbon, that's contamination. So most likely what we're looking at here is carbon contamination.
When you do this focus, what are you really looking for?
I look for this edge to become sharp. See atoms.
What? Just like that. That's wild.
Shortly after the group successfully corrected the aberrations in the TEM, Andrei Krivanik independently achieved the same for Kru's version of the microscope, the scanning TEM. And in 2020, all four were awarded the prestigious Kavli Prize in Nanoscience for accomplishing what's...
This kind of reminds me of, I used to watch the cartoon Justice League, and if you're familiar with Justice League, are you familiar with Atom? And the episode where the android, who created the android? Anyway, there was a mad scientist. He created an android that operated through nanotechnology. So he was chasing Lex Luthor, and the whole Justice League was trying to protect Lex Luthor from the android. And as a last resort, the Atom took himself. He can shrink himself to the size of an atom. So he basically took Lex Luthor and himself into the subatomic universe. That's how small he shrank. I'm not going to finish that story as far as that episode is concerned, but it was pretty interesting. Kind of reminded me, this is what reminded me of that episode, and how they could see atoms. And the subatomic universe was just like a microscopic universe, or the size of atoms, and they showed planets and things like that. It was kind of funny, really sci-fi, but it's this episode reminded me of that, this video. Anyway, I'm gonna finish right here. I saw this really interesting how we can see atoms. We always hear about atoms in our class, science class, physics class, and we've never seen them. I've never seen them until this point. But again, this microscope was created back in the 90s, and I'm just now hearing about viewing atoms. I guess I'm behind, but I thought it's interesting to kind of do a reaction to this. And feel free to let me know what you think. Thanks for listening. I appreciate your time.